All right, I think we're gonna get started. So my name is Adalbert Chang. I'm a software engineer at Box, and today I wanted to talk to you guys about checked complexity with typed simplicity. And essentially what I'm trying to say here is I was looking for a way to build, to structure my programs in a way that was compositional, and that at the very bottom layer was sort of foundational building blocks that we could trust, and it wasn't like a big mess. I was looking for something very simple and foundational, and then we would build more and more complex things on top of it. And so this talk was sort of inspired when I first started programming in industry, where I saw a lot of people create all these objects, and they would talk about things like abstraction and encapsulation and information hiding. And then when they went to go test their program, I would see them mock out like so many things, just so they wouldn't have to like reach out to a database when they test, or send something over a network when they test. And so this seemed kind of backwards to me, because if your code is modular enough, it seems in principle you would be able to just inject or swap out the component you're trying to test, and then you wouldn't very rarely, if ever, have to mock anything. And so when I was looking around, a lot of people were telling me that I should check out this thing called ML modules. So standard ML and OCaml have this notion of they have a special module system that is just really highly regarded, especially by Rob Harper. And so I spent a few months looking and learning and writing some standard ML and OCaml. And I realized one of the big things that's really related to what I was looking for was code and concept reuse. I would like to be able to, and so in the context of that mocking thing, I would like to be able to structure my program around the fact that it depends on X, Y, and Z, and then I should be able to take that entire program, tell it for production I want to use this live database, this live network, this live whatever, and then for testing I should be able to easily swap in a testing thing without having to rely on anything like mocking or anything that messes with like the runtime. Stuff that's very simple. And this also led me down to explore other approaches. So ML modules was a big one for me. Type classes were also a big one for me, and general just functions and functional programming and things. And as I learned more about functional programming, I learned about pure functions, composing effects, reifying errors and side effects as values. I realized that this allowed me to reuse not only the same code, but also the same concepts. And at the very bottom layer, I realized that a lot of the benefits I was getting was due to having an expressive type system. And so that's going to form the rest of this talk. I'm going to walk through a bunch of type system features that Scala has that other languages may or may not have, and show some examples of where I found those features to be useful. So there's going to be a lot of code in this talk, and as I was making these slides, I know I tend to iterate on slides a lot, and I wanted to make sure whatever code I showed was valid code. I didn't want people to be able to like copy and paste my code and then have it not compile. And so I ended up making these slides in Remark.js, which lets you write your slides in Markdown. And these are actually compiled. So all the code you see today has been compiled against Scala 2.11, Cat 04, Time Projector 0.7, using Tut. And so Tut is a tool by Rob Norris, which basically takes Markdown files and then makes sure that all the code blocks you put in there compile against a specific version. So all the code you see today at least compiles. So to start things off, we'll start relatively simple. A necessary tool when we do functional programming is the ability to use functions as values. And so we sort of had functions because we wanted to be able to reuse some sort of basically some computation. We don't want to write the same computation over and over, so we had functions, and then we'll just pass necessary parameters to the functions, and the functions would do the work that we needed. And so we might start off by writing a function that just doubles all the integers in the list, and that's fine, that's relatively simple. And then we say, all right, now we're going to add 50 to each element of the list. And the code ends up being pretty much the same, save for that one part where you actually apply the function to the element, and then you recurse. And so if you don't have functions as values, you end up or doing something kind of strange, like having a class that emulates a first-class function. You end up having to rewrite functions with the similar structure. And so once you have functions as values, and I think this is relatively well known in Scala, you begin achieving a higher degree of code reuse. You don't have to keep writing the same thing over and over again. And to go further with this, Scala also has type parameters, and this is Java has generics. C++ kind of has this with templates. And it's the same problem, right? It's a similar problem, but from a different angle. We write, say, we want to concatenate two lists, and we say let's pretend we don't have type parameters, and we want to concatenate two lists of strings. So you write it, and then you say, now I want to concatenate two lists of ints, but you can't reuse the old one because the inner thing is different, and so you rewrite pretty much the exact same code. And with type parameters, they essentially allow you to abstract out irrelevant information, right? Stuff that is not essential to the algorithm itself, and allows you to, once you've abstracted that away, that gives you a wider surface area for what client code can call your function. So instead of saying, we're going to concatenate two lists of ints, and we're only going to work on int, we're going to say, we don't care about the fact that it's an int or it's a string or a double or whatever. We just care that these two things are lists, and we'll work off that. And yeah, you can, with that, you can pass in a variety of types. So that, again, gives us a degree of code reuse. And then we can combine these two features to have parametric polymorphism and also functions as values to give us really cool and really reusable things. And so one of the things I learned when I started functional programming is that this full write function, which sort of at a glance looks strange, the type signature certainly looks a little complex, but it's highly reusable to the sense that you can implement an incredible amount of list functions, and I believe all the list functions, purely in terms of full write. And so that was really cool to see. So this is just with functions as values and type parameters. So to go slightly deeper into type parameters, you can think about type parameters as like universal quantification in logic. Basically, when you have a type parameter, you can say, so to apply here in the trait, it says, for any a you give me, I will produce you an a, right? And this is essentially, you can choose any a you want. And if you choose an int, if you choose a double, if you choose string, whatever, I can satisfy it. Because I don't care about what a you choose. My function or my implication works regardless of whatever a you may choose. You can contrast this with existential quantification, right? And corresponding to types, there's existentially quantified types. And this manifests itself two ways in Scala. The one I'm going to talk about now is in the form of type members. And here, instead of saying for all a my function holds, you're saying there exists some a that I'm not going to tell you, but there exists some a such that my function works. And so from this angle, it becomes not you choose any a you want, it's I have chosen an a, and you don't know what it is. And so here we see when we try to do the same thing we did in the previous slide, you can't do it, right? Because you're asserting that the a in there is an int, but the type checker sees that, well, it's abstract. I can't guarantee you that that a is ever going to be an int. So it doesn't work. And this sort of leads to the idea that existential quantification is information hiding, right? You have something that's relevant to your algorithm or to your computation, but it's something that they should not have to know about. At least they should not know about the concrete form of it. And we can see an example where this. So the example I have is stack. And so we have two sort of types in play here. One is a universally quantified a, which is known to you. This is something that you do want to care about, right? Because if you have a stack of int, you want to know that the stack contains an int. So it can be universally quantified. But the representation of the stack you should not care about, right? I've given you some API, and you should be working against that API. You should never actually depend on what implementation the stack is using. So we accidentally quantify over the representation. And so as an example, if we take this sort of stack module as a parameter, we know that it's an int, so we can push 1, 2, 3 against empty. But what we can't do is sort of say, well, I bet the stack is a list under the covers, so I'm going to just push 1 onto the supposed stack to list 2, 3, 4. And the type checker will be like, no, you can't do that, because for the same reason as before, it doesn't know what representation you're going to use, right? Because it's existentially quantified. And so what this allows you to do is prevent the type is still exposed in the sense that people can get a hold of a value of that type, and this is what empty gives us. But they are not allowed to do anything with that type that you don't allow them to do. And I've used this before in a similar way, but but this also enforces that they never depend on implementation detail they don't care about. And so I should be able to take a completely different implementation of stack and then give them that, and their code will all work, because they've never like leveraged the fact that the representation under might be a list. I can change it to like a vector someday, and their code will still work. Moving on to a different type system feature, and we'll talk about kinds and higher kinds. So to give a brief introduction, you can sort of think about kinds as the type of types. And one way I think I heard Daniel put it once was types are the values as kinds are the types. And we usually talk about kinds in this notation. We use a star, and you can read it as type. And so the kind that everyone's sort of familiar with is just a plain type. And it's a concrete type that you can have a value of. So it's integer, character, a list of int, whatever. And then you can have type constructors or unary type constructors that, given a type, will give you a type. So list vector future, you give it an int, and it will give you a future of int, or you give it a string, and it'll give you a vector of string. So given a type, it will give you a concrete type. And then you can imagine the same thing for binary types and three-array types and so on. And so this leads us to higher kind of types, something that not many languages support. And as far as I know, the languages that are in use in industry today that do support this are probably just Scala and Haskell. And essentially, higher kind of types are types that abstract over type constructors. And so as an example, so these are often used in the context of type classes. And as an example, we have this idea, say, of a functor, which abstracts over a type constructor. And if you look at the kind that I wrote there, the kind is, given a type constructor, I will give you a concrete type. Right? And so functor there, let's see if my mouse works. Yeah. So it takes a type constructor, and then it has the map method on it. This is distinct from if we, like, say, move the A up here, because then you would have to define, like, the instance for if we said F was list, and then we said A is, we would have a different instance of it for a list of int, list of string, list of double, and so on. Whereas if we're able to just parameterize over the type constructor, then we're saying we fix F to be list, and then we make map parametric entirely over A and B for any choice of A and B that you choose. And so this gives us essentially generics of a higher kind, right? It gives you a higher degree of being able to abstract in your code. And as a sort of example, because all the code in here has been run through a compiler, I've defined a functor that just given the list, so it's not a list of int or a list of string, it's just the list type constructor, and I have an actual type back. And this allows us to achieve something really, essentially, having just like plain the plain universal quantification that we saw before, it gets us things like list concat, reversing of a list or whatever. But being able to now talk about higher kind of types, to be able to abstract over type constructors, gives us a very large degree of code reuse. And so I don't want to get too much into detail here, but here we're saying we have a list of A, and then we have a function that goes from A to some g of B, right, where g is free here, or is universally quantified here, such that g has this instance. And so essentially this instance is, it abstracts over things that, given two independent values in the same context, you're able to take those things and combine them together. So you can imagine it's future, where you zip the futures together, or it's list where you concatenate, or option where you combine them only when they're both sum. And so we write this function once and for all against a list of A, and then for some sort of G. And we can use this in the context of option, where our G becomes an option. And so let's say we try to parse an int, and then when we give it a list of everything ints, we get, if we parse all the ints successfully, we get a sum of the list of results. If anything fails, then we just get none back. And that's just the behavior of options applicative instance. That same exact function allows us to essentially do sort of like a fork join thing, where we take each element of the list, fork off a computation, and then eventually collect all those. So we fork off many futures, and we're able to collect all those futures into a single list. And then that exact same function can also be used with lists and many other data types to do a variety of things. And I've only written traverse list once. And in fact, you can further abstract, make that more abstract, where you don't fix it to be list. You can fix it to be a different type constructor, but I won't get into that today. And the last thing I wanted to talk about was embedded DSLs. And I think over the past 2-3 years, the idea of embedded DSLs and specifically the encoding using free monads has been pretty popular. And essentially the idea is you build an AST of a DSL that your domain is in. So maybe you're writing a DSL for a database access, or you're writing a DSL for talking to HTTP. And the core idea, the thing that lets you reuse code a lot, is it's separating the structure of your program from the actual interpretation. And you can think of it sort of as like a mini program inside your program, right? Inside, you have like this small program that knows how to talk to a database and only to a data, and that's all it knows how to do. And it lives inside your actual program, the source file that you're writing. And then you can pass all these ASTs around in your program, never actually interpreting them. You just have a bunch of these data types, these values, these structures describing what you want to do, and you don't actually interpret them until like the very end of your program. And the usual encodings of this come up in like free monad, free applicative, and finally tagless. And because there's been so many examples of free monads and free applicatives, there's countless number of talks and documentation around that. I decided today that I was going to show or run through briefly the finally tagless approach of doing an embedded DSL. So we can start by, so the example I'm going to do is basically a read-write, something that can read something, maybe off console, maybe off a file, maybe off a list, and it's something that can write something. So it has two things it can do, and then I have the monad there to say that, essentially to capture the fact that maybe we want to write something that we read, so to capture the dependency between the two, possible dependency or bindings. And then so that's gonna act as our interpreter. And then we're going to write another data type called RW that, when given an interpreter, will actually produce or run the effect, right? So you can imagine you have a read-write structure or an AST, but it hasn't been interpreted yet, and so nothing has actually happened. It purely stores structure. And you can define a monad for it by virtue of basically delegating all the work to the interpreter. But again, the RW data type is not interpreted yet. And then you define some smart constructors that correspond to the evaluator you have. So here we have read, which doesn't take any parameters and just gives us a string. And then we can write, which given the string, we'll presumably write it and won't have any meaningful value to return to you. And so similarly, we have the read and write smart constructors that construct RW instances. And so we can construct a program that says we're going to read something binding to X, we're going to read something binding to Y, we're going to concatenate those two strings that we just read, and then we're going to write that back out. And so this returns immediately. This doesn't do anything again. And so we have this RW unit that has no meaning whatsoever. And then we can write an interpreter for that using the console. So ID or id is sort of at least the encoding here is defined as just a type alias, where type ID of A is just A itself. So it's essentially, you can think of it as any plain value you have, right? ID of int is just equal to int. ID of list of string is just list of string. And then to read, you use the standard in. To write, you just printline it. And so we have an interpreter now, and we take the program we had before, and we can run it against the standard I/O interpreter, and then it'll read two things off console, and then it'll print to console. We can also define a different evaluator, which uses the state monad, which I capture it here as two lists of strings. One of the lists of strings will contain everything that's going to be fed in. So each time each time it reads something, I'm going to give it one element off the input list, and each time I write something, I'm just going to concatenate it or prepend it to the output list. And then you're able to read and write by by just passing in a new state and the result of what happens when you read something or what happens when you write something. And that exact program that we had before, the one that I defined like 2 or 3 slides back, can be run against this interpreter. And so this part just gives us an instance of state that's now expecting, tell me what the initial state is, and then I'll run all your instructions against that state. And here I'm giving it this initial state over here. And so we can take that exact same program and run it against a completely different interpreter. And now we're able to, and so you see here, because I only read twice, it didn't actually read these two, but it did read these first two. And then it wrote hello any Scala to the end. And so we're taking that exact same program and running it against a completely different interpreter. And so you can imagine if you pass around a bunch of these ASTs around your program, at the very end of your program, you can say, all right, now for production use, we're going to run it against this interpreter, and for testing use, we're going to run it against this interpreter, and you can make sure everything is good. And in summary, plain functions just allow you to reuse computation, stuff that is fairly common. Functions as values allow us to write very highly generic combinators, so stuff like fold right, stuff like map, flat map. Type parameters allow us to abstract away unnecessary details, so you don't care if it's a list of int or a list of string when you reverse it. Abstract type members allow you to enforce the hiding of irrelevant detail that sort of will still be exposed, but you don't actually want them to know what it is. Higher kinds essentially allow you for higher order abstraction, being able to abstract over things that you otherwise would not be able to. And writing all these EDSL such that you separate the structure from the interpretation allows you to run the exact same structure against a variety of interpreters. And so some of the stuff that I found was really useful when I was writing or learning about this were two related papers, which essentially they start from a very plain lambda calculus, and then they slowly add on more and more type system features and show how what degrees of abstraction and polymorphism and reuse you can get as you add more things. And then there was also a really good talk by Edward Komet, I think last year, that's on YouTube, talking about how you can achieve also a lot of code reuse by using type classes. That's all I have.